In this video, we'll look at the second fundamental theorem of calculus. The AP standard for this is FUN-5.A.2. This standard gives us the second fundamental theorem of calculus. That is, if f is a continuous function on an interval containing a, then all this right here is just equal to f of x, where x is also on the interval. And here's a quick reminder of what the first fundamental theorem of calculus was. The first fundamental theorem of calculus said that if f is continuous on the interval from a to b, and capital F is the antiderivative of little f, then the integral from a to b of little f of x dx is equal to capital F of b minus capital F of a. So in other words, a definite integral is just the antiderivative of the function inside the integral. The function is then defined at the top boundary, b, and then you subtract, and your function is defined at the bottom boundary, a. So we can see that the second fundamental theorem of calculus looks different than the first fundamental theorem of calculus, but the second fundamental theorem of calculus is actually based on the first. Here's how that works. So we can start by defining capital G of x as being the integral from a to x of f of t dt. F of t, in this case, is a continuous function, and little a is just some constant. Then we can rewrite capital G of x as being capital F of t from a to x, and we can do that by the first fundamental theorem of calculus, where capital F of t is defined as the antiderivative of little f of t. That means that capital G of x is just equal to capital F of x minus capital F of a. So then let's take the derivative of capital G of x. That would be the derivative of the integral from a to x of f of t dt. Well, we just showed that that integral was equal to capital F of x minus capital F of a. And then taking advantage of the way that we defined capital F of x, the derivative of capital F of x would be little f of x. And then the derivative of capital F of a, which is just a constant, would be 0. That means that the derivative of capital G of x is just equal to little f of x. So there you go. We started with the left half of this equality, and we showed that this is equal to the right half of the equality. Therefore, we have proved the second fundamental theorem of calculus. So then you might be wondering, what's the point? This theorem is what a lot of calculus is based upon. The first corollary of this is that every single continuous function is the derivative of another function. Or in other words, every function is the antiderivative of a continuous function. And the second corollary is that integration and differentiation are inverses of one another. They undo one another. So here's a quick example. Let's say that f of x is equal to the integral from 0 to x of cosine of t dt, and we want to find f prime of x. As a side note, this is called a function defined by integral, or we can call it FDBI for short. We'll spend a few days just looking at different FDBI problems, and your performance final is going to be specifically on an FDBI problem. So this and the following examples are something that you really want to pay attention to. Well, we can find f prime of x two different ways. The hard way is by not using the second fundamental theorem of calculus. To do that, we would find f of x just by evaluating the integral. The antiderivative of cosine of t is equal to sine of t, and then the boundaries from the integral went from 0 to x. This is just using the first fundamental theorem of calculus. So then we want to plug in our boundaries for t. The top boundary was x, so that would give us sine of x, and then you subtract and plug in your bottom boundary, which was 0. Since sine of 0 is just 0, that would give us sine of x. Now we can find the derivative. F prime of x would be the derivative of sine of x, which would be cosine of x. So cosine of x is our answer. Now let's look at how much faster it is by using the second fundamental theorem of calculus. We want to find f prime of x, which would just be the derivative of that integral. Well, the second fundamental theorem of calculus says that the derivative of the integral is just equal to the function itself with that top variable plugged in for t. So then the function inside the integral is cosine of t. the bottom boundary is a constant, 0, and the top boundary is the variable x. So all we have to do is plug in x for the t inside of the cosine function, and that would be our answer. So you can see that we get cosine of x either way, but by using the second fundamental theorem of calculus, we get to the answer very quickly. Here's one more example, just to give you a little more intuition for how a function defined by integral actually works. Let's define capital G of x as the integral from 0 to x of 2t dt. If we use the first fundamental theorem of calculus, we can evaluate the integral by finding the antiderivative of 2t, which would be t squared, and we want to evaluate t squared from 0 to x. That would give us x squared minus 0 squared, which is just x squared. So let's think about what g of x actually is. G of x is defined by the definite integral of a function, and we know that the definite integral is just the area under the curve. So capital G of x is the area under the curve of 2t from 0 to x. You might notice that the area under this curve is just a triangle. Let's say if we want to evaluate g of 1. G of 1 would just be equal to the integral from 0 to 1 of 2t dt. Since that area is just a triangle, we can use the area of a triangle formula, which would be 1/2 times base times height. The base in this case is 1, and the height is twice that value, which would be 2. So g of 1 is just equal to 1. If we find g of 2, that would be the integral from 0 to 2 of 2t dt. That'd be the area of the triangle with a base of 2, and the height would be twice the base, so the height is 4. So g of 2 would be equal to 4. So then let's just extend this concept of using triangles to evaluate g of x. So capital G of x would be equal to the integral from 0 to x of 2t dt. And using the area of a triangle, we'd have 1/2 times the base, well the base is just equal to x, times the height, which would be twice the base. That means that g of x would be equal to x squared. And notice, that's what we found by using the first fundamental theorem of calculus up top. The important takeaway from this example is that there's more than one way to evaluate a function defined by an integral. We could do it by using the first fundamental theorem of calculus, and if we have access to the graph, then we could do this geometrically. And even more specifically, if we don't have access to the equation itself and only have access to the graph, we could use area under the curve on the graph to evaluate g of x. So that's it for the notes on what the second fundamental theorem of calculus is. In the next video, I'll show you a few examples on how we can apply it.